And it's time for me to invite the second speaker, Professor Samsuzana Aziz from Department of Biological and Agricultural Engineering, University, Putra, Malaysia. The topic of the presentation is Flying LoRA, IoT Gateway for Agricultural Applications. The floor is yours, Professor.
Assalamualaikum and a very good morning, everyone. Thank you so much for having me today. I'm Samsuzana Aziz from Universiti Putra, Malaysia. First of all, I would like to thank Professor Eric Fron and his team for doing the tremendous job organizing this conference. I think it will be very interesting for these first 2 days of the conference. Today, I would like to give sharing some of our recent field trial on flying LoRA IoT gateway for agricultural applications. Doesn't move. It didn't work. Okay, just would like to give a little bit of background of my research. For the past 18 to 15 years, I've been working on agricultural engineering research. In response to the discussion that we have yesterday on the marine sciences and biologies, we in ag engineering we also doing very similar approach. For example, this one, I just want to show that we also do the plant phenotyping instead of, trying to develop the 3D models of the coral reefs in the marine science. We, in the agriculture, we also develop the 3D models of the plants so that we can extract the informations of the plants for the breeding programs. Only that I would like to highlight here, the work that we have done here is using structure from motion, which is very similar to Professor Michael Buneman that presented yesterday. But this one, we were using unstructured 2D images, meaning to say we collected it from a simple devices, a smartphone, reason being because most of the farmers and breeders, they are very reluctant to invest into a new equipment, but everybody has smartphone. So using their smartphone, collecting multiple images from the smartphone, we've been able to reconstruct the 2D model of the plants or crops for breeding programs to extract the plant information like height, leaf area index, biomass, and etc. Also, in response to the discussion that we had yesterday, I also would like to share some of the work that we've done for the questions that how much do we need to sample in our monitoring. In agriculture, the sampling strategy is very much established. This is one of the work that we've done a couple years ago, long time ago, that we develop an adaptive sampling strategies for agriculture, where the concept is you want to go samples in higher resolution at the area that has higher variability in the field, and the area that has a lesser variability, you want to sample it less. So the work that we done back in the United States has been published in the transaction of the American Society of Agricultural and Biological Engineers. If you think that it will be helpful in your studies, I will be happy to share with all of you. For today conference, I'll be very focused on one of our recent studies. Well, I might say it's a field trial to promote the utilization of IoT among the plantation, among the growers. So we'll be very focused. We'll give you some introduction of the technology, the LoRA technology, which is the wireless communication technology that we adopted for the IoT deployment in the plantations. And then what the LoRA IoT consists of, how does the LoRA works for agricultural, and what makes it so difficult, and the challenges that we've been facing, as well as our case studies and some conclusion and way forward. So the LoRA low power wireless technology can be divided into three according to the range of the data transmission. The short range, the first range is between 10 to 100 meter, which is, we call it wireless personal area network. You probably have heard Zigbee, Z-Wave, Bluetooth Low Energy is one of the example. And then the second categories is the short and medium range covered between 100 meters. It's like Wi-Fi that when we usually use daily, and we call it wireless local area network. So the longer range, or from medium to long range, we categorize it as we call it LoRa, long range communication. And one of it is LoRaWAN. There's many technology like Sigfox, NB-IoT, LTE. So those are the ones that fall into the categories of wide wireless area network. So in agriculture, why the LoRa low range wireless area networks are being very attractive is because it utilizes very low power consumption, because it can transmit very further away. It's a long range, so you can cover a large area of agricultural field, and then it has a very low power consumption. That means you can use the end devices much longer and reduce the maintenance. But of course, it's come with some drawbacks where you need to compensate the data rates of the data that you want to transmit. So when it has a very low power consumption, then the cost of the technology will become lower. That's another attractive features for agricultural application. Just to give some overview of the LoRa operating frequencies across the regions. For Malaysia, we are using 920 to 925 megahertz. Particularly in Malaysia, the one that we use is 923 megahertz. So it depends on your country, what's carrier frequency that you subscribed for the LoRa communications. I believe in Saudi, it will be very similar to Europe and India, which is around 866 megahertz frequency. So the availability of the LoRa networks and roaming capability across the world has been tremendously, covered. Some of the countries, about 150 countries, has already have the network operators locally, and around 27 countries already have the roaming capability of the LoRa within their public networks. So what LoRa consists of? So it's just like a normal IoT architecture. So LoRa has the end devices, or we call it LoRa device. Usually it consists of the sensors or actuators where you transmit the messages to the gateway, or we call it server, or if you might want to call it server. So LoRa gateway is the server that receive the data from the end devices. And in this particular case, LoRa technology can transmit theoretically up to 10-kilometer range. And then those data will be transferred to the network server and then also to the application server for further analysis. So how does LoRaWAN works for agriculture? So it's become very attractive because it can cover up to 10 very long range data transmissions. And because of you can transmit simple data, but it's very useful in agriculture. For example, just the soil moisture, the soil condition like pH, EC, the nitrogen content of the soil, and pK, and also temperature. That is very crucial for them to measure and monitor for more efficient management of the farm, especially in controlling the amount of inputs like water and also the fertilizer. Okay, so theoretically, it can goes up to 10 kilometers with a very minimal line, with very clear line of sight. We have also did a trial with the Malaysian Technological Standard for Communication and IoT in Malaysia, where we've successfully transmitted the data across the sea, and it goes far beyond 10 kilometers. It goes up to 23 kilometers across the sea. It's because of the clear line of sight. So it's pretty much very straightforward. What we did was we hook up the receiver of the LoRa nodes on top of the building on the mainland, and then we have this small island that is used for research purposes for marine science, that they need to collect data continuously. So we put the transmitter nodes or the sensor nodes on top of the island to transmit environmental data continuously, and our result shows that it can go up to 23 kilometers with very acceptable signal to noise ratio. So let's come back to the agricultural applications. We have tested the LoRaWAN communication in the soil monitoring of oil palm nursery. Also, we successfully deploy the LoRa nodes across the nursery because the main reason the line of sight is very clear. The plants is not that tall, just less than 1 meter up to 2 meters. So line of sight is very clear, so you have no problem with the data transmission. And then later in 2019 BC, before COVID, then we do another test in the oil palm research plot on the campus, where the trees is a bit taller. We call it young palm trees, and it's about like 4 to 5 meters height. So now it started to have some canopies. So when we put our sensors under the on the soil, we still can receive the signal from the sensor nodes to the gateway, but some of the nodes we lost the data because of the occlusions of the crop canopies, the plant canopies, and also because of the altitude and elevations of the land itself. Okay, so the challenges when we try to deploy this wireless communication IoT in the plantation is that when you have interruptions of the line of sight from the transmitter and the receiver. So as the crop is small, you have no problem, but then all palm trees can, the life cycle is around to 25 years old. So when it's get taller and taller, you will have a more denser canopy that will interrupt will give obstructions to the data transmission. For your information, in Malaysia, we have around 5 million hectares of old palm plantation size. It's huge. For us to cover the whole plantation is almost impossible. Not only because of its canopy occlusion, but also due to the undulating elevations. Like if you see at the back, further back of the photos, you can see like a hilly and mountainous areas that you definitely will get a signal obstruction. And another problem is that there is no existing infrastructure for you to install the gateway or the gateway or the server for you to have the data. So that's another challenge. So before we convince the plantations to build the structure to network their farm, we already knew that even if they have the structure and invest into money to put to cover the networks in the plantation, you still have problems in terms of the occlusions and etc. Just like what I've mentioned before. So here come our suggestion is that instead of you invest into a fixed infrastructure, we can use drones to go to the area where we want to collect the data, go closer to the area when we want to collect the data. So here's some example of our recent studies after COVID. The one that we did before was before COVID, when the crop much not that high. Now after the COVID, the crops has become taller. And when we repeat the experiment, we basically fixed the gateway in one of the existing building nearby the plantation, which is around 90-meter altitude. The area was around 31 hectares, about 5 to 6 meter tall trees. And then it is like 10 to 15 years old palm trees. Okay, so we fixed the gateway at the nearby building and then try to get the data from the sensors that we deploy across the plantation plot. So these are the specification of the LoRA technology that we use. It's pretty much very standard. It's out there and it's ready to be adopted. The LoRA gateway that we use is an 8-channel outdoor LoRA gateway that is very powerful, has been tested to be used in other industries, like in the smart cities, but for agriculture, this is the one that this is the first trial that we're trying to do. One channel can hook up around 200 end devices, and we have 8 channels, so it can hook up close to 2,000 LoRa devices. Okay, so from our studies, it shows that as the tree has become taller, the occlusions become denser, the canopy become denser, and we miss a lot of data from many nodes when we try to transmit the data at below the maximum transmit power. So it's very also important for us to use a very minimum transmit power to conserve the energy, to lessen the energy that is used for the end devices. So in our case, in this trial that we did, anything below 20 dB transmit power, you will not get any data. Okay, so so we try to recover this using flying drone gateways. What we did was we hook up the gateway on top of the agricultural quadcopter drone. It's a commercialized drone used for agricultural applications. specifically for data surveillance and also for spraying. So they're spraying the fertilizer in the plantation using similar drone. It can have a maximum takeoff weight around 25 kilogram, and it's not that heavy. The frame weight without batteries and without all the payload is around 5 kg, and our gateway is just 1.2 kg, and it's easily can carry the gateway. So it uses a LiPo battery, and it can operates around 20 minutes flying time. So we carry up, you can see, we carry up the gateway. I also sensor group for that is in the gateway is 300. Just show some videos of the flying drones gateway going closer to the plantation, and we can see the canopy of the palm trees from the remote control of the drones. So from the task that trial that we've conducted, we obtained a significant improvement in terms of data transmission recovery at location where data were lost in the previous case where we fixed the gateway in just static location. In fact, for all nodes that we deploy in the plantation, we successfully transmit maximum data payload of 50 dB. At the minimum transmit power of 6 dB, which is preferable in smart farming applications. So just very quick conclusions on the recent trial that we've done. Improvement with respect to the fixed gateway is notable, where the communication recovery was obtained by using a flying LoRa gateway, which is able to move closer to end devices. And we also shows that the performance benefit in terms of the power consumption can be enhanced and at the end device, which is very important for smart agricultural application. So as the future work, we envisage to extend the work through AI-based approaches to dynamically and optimally configure the flying LoRa gateway on demand and according to the plantation situations. Lastly, I would like to thank the H-Drone Robotics Industries, which is the startup company focusing on drones applications in Malaysia, as well as LoRaNet, one of the company for LoRa, one of the provider for LoRa services in Malaysia, for helping us to do the trial. So yeah, I'll take questions from them. Thank you.
Thank you for the exciting talk. It's time for questions.